Okay, this video is a little bit of an extension beyond the normal grade 9 curriculum, but something that those of you that are interested in electricity might like. We're going to talk about how we combine resistors to solve more complicated circuits. So here we have two basic options. We have resistors in series, as is shown in this diagram below, or resistors in parallel. To combine resistors in series, we can simply add the individual resistors. To combine resistors in parallel, we have to use a more complex formula where we add the inverse of each resistor. So if I had two resistors, 10 and 20, and they're in series, and I wanted to represent them by just one resistor instead, I could take the 10 plus the 20 and represent them by one 30 ohm resistor. A little more difficult than that, if I had one resistor, I wanted to represent these two parallel resistors as one resistor in total, I could add their reciprocals. And then take the reciprocal of that. Oh, what did I do there? There we go. And I would represent those by a 6.67 ohm resistor. This is really useful because if we have a complex circuit like this one, and we want to solve it, we need to make it into either a series or parallel circuit so that we can solve it more easily. So how can we do that? Well, let's just try and ignore some of the stuff we did over here so we can focus on the circuit at hand here. Okay. Now, to get this into a simple circuit, the first thing I'm going to do is I'm going to combine these two resistors that are in parallel into one resistor to simplify it a little bit. So, since they're in series, I'll use the equation that the total resistance is equal to the sum of the individual resistances. So 5 plus 15 is 20 ohms. And so I can redraw my circuit with my new resistance like this. Now I don't really have a good strategy for solving this circuit because it's still a mixed circuit. So now I'm going to combine these two resistors in parallel using my other formula. So I can replace them with a 6.67 ohm resistor because that is the equivalent effective resistor. Now why is this useful? Well, let's just put a voltage on this battery and see how this helps us. Now I have a simple series circuit that I can solve. So I can say 20 volts is equal to my V1, calling this my resistor 1, plus my 2, V2, and then I can use my trick where I say V1 is equal to 10 ohms times the current, and V2 is equal to 6.67 ohms times the current, recognizing that the current is constant everywhere in the circuit and using Ohm's law. And replacing those two things, I can get 10I plus 6.67I is equal to my 20 volts. And now solving, I get a current of 1.2 amperes. Now I recognize that this resistor in the circuit has remained unchanged through all of the changes I made to this resistor as I did all this simplification. What that means then is if this current is flowing through it at 1.2 amperes, and then using Ohm's law, V1 equals 10 ohms times I2, or I, which is 10 ohms times 1.2 amps, or 12 volts, I can get a bunch of information about my original circuit that when I put it back onto my original circuit is going to allow me to solve that circuit much more easily. So this is basically what my original circuit looked like. That was 10 ohms, that was 10 ohms. One of these was 15, 5 and then 15. This one was 5 ohms, and this one was 15 ohms. So with that in hand, that makes this 12 volts. This current was 1.2 amps. And now I can start using some of what I know about circuits to solve this a little bit more easily. If I go up 20 here and down 12 here, then I can figure out what voltage I must have at resistor 2. I went up 20 volts, then I went down 12 volts, then I was left with resistor 2. So resistor 2 is 8 volts. Using my resistance and my voltage at resistor 2, I can find my current. Of 0.8 amps. And now using my current law, recognize that I have 1.2 coming in here and 0.8 of them are going down here, so I have like 12 cars coming in here and 8 of those cars are going down this way. I can figure out how many cars must be going down branch 3. So that means that this has to have 0.4 amps, and this has to have 0.4 amps. Finally, at locations 3 and 4, I can use Ohm's law, respectively. Using a current of 0.4 amps and 5 ohms at the first resistor to get me 2 volts, and using a current of 0.4 amps and a resistance of 15 ohms at the second to get myself 6 volts, I can get the missing pieces of information for my circuit. I know that was fast. I've gone through how to do this in some other videos a little bit, so I'm assuming you've watched those other ones before you started this one. And I am considering this an extension, but as difficult as that might have seemed, and maybe this is a little bit hard to wrap your head around, but it's a heck of a lot easier than trying to use all of this algebra to try and solve a similar circuit. So this combining resistor method is a little bit more reliable and a little bit simpler in terms of trying to solve these complicated mixed series and parallel circuits. So that's just an overview. If you, like I said, I'm looking for something that goes a little bit beyond the normal grade 9, then that's something to challenge you.